All right, so it's Wednesday, and we will cover clustering, K-means clustering, but with kernel functions. So we're going to be clustering with kernel functions. Okay, so review. When we covered the K-means algorithm, the way it works is you kind of start off and you say, I'm going to look for K clusters. All right, you declare how many clusters you're going to search for. And then you randomly assign points in your data to the clusters. Once all the values have been assigned, then you calculate the centroids of each cluster. And after you calculate the centroids, you reassign the points by saying which one has the smallest Euclidean distance. And then you iterate back and forth. You reassign, you recalculate the centroids, reassign the points, recalculate the centroids, reassign the points, and you keep going back and forth until you reach convergence. So, so here we have some random assignments here. All right, so I've got some data. We randomly assigned them to 3 clusters, black, red, and green. And then we'll let the K-means clustering algorithm run. So here is the centroids of these random assignments. And we'll say, all right, which data points are the closest? So we've got the red ones get associated there, the black ones get associated there, and the green ones get associated there. And then we do this. And we recalculate the centroids. All right, so here are the centroids, and we say, okay, well, let's reassign the points based on which centroid is the closest. And this is the change. So these points get reassigned to green, and we recalculate the centroids, and then we say, all right, let's reassign the points to which centroid is the closest. Those get reassigned, and we recalculate the centroids. All right, we say which points are the closest to the centroid. Those get reassigned. We recalculate the centroids, we reassign points, and this time only like a few points changed. We recalculate the centroids, and then we see if any points get reassigned and none do, so that means we have converged. Okay, so looking at this from the start, we started off here, calculate the centroids, reassign points, recalculate, reassign points, centroids, points, centroid, points, centroids, points, centroids, and then when we reassign points, nothing changed, and thus we have reached convergence. So that's K-means clustering. I think, I hope, well, I know you guys just saw it on Monday, but I hope this feels at least familiar enough to be kind of review for now. And so now what we are going to do is we're going to do kernelized K-means clustering, okay? All right, so we saw kernel functions earlier when we were talking about SVM, okay? So when we did SVM, we talked about the idea of taking 2-dimensional data and then projecting it into like 3 dimensions, okay? And with SVM, it was like you can't draw a linear boundary that separates the points in 2D, but if you project it into a higher dimensional space, you can find a linear hyperplane that's going to separate the values. And that's what we did in SVM. Here we can apply the same kind of idea of using a kernel function, which is equivalent to taking the inner product after we transform our data from 2D into some higher dimensional space. So we're going to take our vector xa, we apply a function phi that's going to transform from 2D into a higher dimensional space, and then take the inner product. Now, if you have the linear kernel, then phi is the identity function, and basically the inner product of of this inner product of phi of xa is just going to be the inner product of xa and xb. Okay. So, so that's just going to be xa transpose xb or xa dotted with xb. That's what we're going to get. Okay, but I think this is the transform in the kernel that we saw when we talked about SVM when we went from 2D to 3D space. Okay, So here we said our data points are in x1 and x2, and then when we apply the transformation function phi to it, it's going to go from 2D to 3D space, and the third coordinate is going to be x1 squared plus x2 squared. And so if I apply that to the vectors xa and xb, okay, phi applied to xa will go become xa1, xa2, and then it's got the two coordinates squared, so it's going to be xa1 squared, xa2 squared. And we're going to do the same. We're going to apply phi to xb, so we have xb1, xb2, xb1 squared, and xb2 squared. And if we take the dot product of those two vectors, we're going to get the sum of xa1, xb1. Okay, and then we look at the second components, xa2, xb2. And then we look at the third component, which will be xa1 squared and plus xa2 squared times xb1 squared plus xb2 squared. Okay. All right, and what we see is we recognize this, xa1, xb1 plus xa2, xb2. That is the dot product of xa and xb themselves. And this we recognize as the squared norm, okay? Xa norm squared, and this is xb norm squared, okay? And so this thing times this thing is the product of xa norm squared and xb norm squared. All right, and so so this kernel function, which is this, is the equivalent of applying a transformation function phi, which creates this, and taking the inner product of the transformed vectors. All right, here is another example, okay? So this is what's known as a polynomial kernel. The polynomial kernel in the general form is, you'd say the kernel function is going to be c plus xa transpose xb raised to the gamma power. If you take c equal to 0 and gamma equal to 2, then that's what we call the quadratic kernel, and that would and it is equivalent to using this phi transformation. If you apply any other values, that you're going to have a different phi transformation with more terms here. And so here, if I apply this transformation to xa, I get xa1 squared, and here I get xa2 squared, and I get the square root of xa1, xa2, and here I get xb1 squared, xb2 squared, and the square root of xb1, xb2. And when I take the inner product or the dot product of these two things, we get xa1, xb1 quantity squared, right? So if I do xa1 squared times xb1 squared, I can simplify that as xa1, b1 quantity squared. Same thing over here, I get xa2 squared times xb2 squared, which is equivalent to that. And then this times this, the 2's combine, and I get xa1, xa2, xb1, xb2. And if we have a sharp eye, then we can recognize that this is, this whole thing here is equal to this quantity squared. And each of these are just, and this whole thing inside here is the dot product or the inner product of xa and xb. So it's just xa transpose xb quantity squared, okay? And so again, this kernel function here is the equivalent of applying some transformation, this transformation, to xa and xb, and then taking the inner product. All right, and again, the point of these kernel functions is not to like literally find the transformation function and then do the inner product, but we can just kind of apply the kernel function. Okay, we don't have to necessarily know exactly what this phi transformation function is. Okay, so we have other kernels. So the polynomial kernel, which we saw on the previous page, but the general form has, you can use any constant c and any constant gamma. And then we have the Gaussian kernel, also known as the radial basis function, and it looks like this. Technically, this value, this kernel uses a transformation function that transforms it into infinite dimensional space because it uses the Taylor expansion, the Taylor series for the exponential function, which is infinitely long. And so, you know, we cannot actually comprehend the, maybe comprehend's not the right word, but we can't actually write out the transformation function with all of its terms because it's infinitely long. So, you know, all of these kernel functions that we look at, they are inner products of vectors after they've been transformed by some function phi. But again, we don't need to think or know what that transformation function phi is, okay? And so what we can do is, because this kernel function is equal to this times this, okay, is just an inner product for some arbitrary transformation function, a kernel function can be used as a substitute for an inner product in the original space, right? So if we see this and we say, what if instead of using x, what if I applied a transformation function phi to x and a transformation function phi to xb, okay? Without even, I can just say, well, that thing, if I applied phi to here and phi to here, then I can replace that whole thing with the kernel function of xa and xb. And I don't actually have to go through the process of applying the transformation phi function to xa and the transformation phi function to xb. Okay, so let me show you what we're going to do, okay? All right. When you do K-means clustering, what we do is we take the points that are currently assigned to a cluster and we find the centroid. And then in the next step, we find the distances from each point to the centroid, okay? And based on the distance to the centroid, we're going to say, all right, this point is closer to this centroid than it is to this centroid. Therefore, this point is going to get assigned to this cluster, okay? Because we look at the distance from the point to the centroid, okay? So what we're going to do is we're going to try to find a way to express the distance to the centroid, all right, as an inner product, not an inner product, but as kind of a, we're going to find another way to express the distance to the centroid, okay? So the squared distance to a centroid, okay, the squared distance to a centroid can be expressed as this, right? We take the current xn value, the centroid mu sub k, and we say, all right, so here's the vector xn minus mu sub k. That's the vector that joins these two things. And if I dot that with itself, basically I get the squared distance, right? So if I do xn minus mu k transpose xn minus mu k, you know, I'm basically taking each, you know, I'm taking the difference in the x1 component squared plus the difference in the x2 component squared plus the difference in however many x components you have. You're squaring that and you're adding them up. That's going to be the squared distance from this point to this point. And we're taking the distance from xn to the centroid mu sub k, okay? So that's this distance. So the centroid of cluster K, mu sub k, that is equal to basically the sum of all the x's that belong to cluster K divided by how many points belong to cluster K. And that can be expressed using the assignment vector, right? So we have a vector z, which is 0 if a point does not belong to cluster K, and 1 when the point does belong to cluster K. So when we do z times xj, only the points that belong to cluster K will have z equal to 1. So we're going to be adding up the x's that belong to cluster K. When x sub j does not belong to cluster K, this quantity is 0. So these get zeroed out, and we are not adding them to the, they will not be contributing to the sum in mu sub k. So we're going to do that. We add up all of the x values that belong to cluster K, and we divide by nk, which is how many points, or that's just the sum of the zk's, is how many points belong to the cluster, okay? All right, the next slide looks absolutely crazy, at least in my opinion. It looks kind of crazy, but all I'm going to do is I'm going to take this quantity, this summation thing, and I'm going to plug it in for mu sub k. So right now I've got the squared distance from some point x to the centroid is this, x minus mu sub k transpose x minus mu sub k. I'm going to plug that, I'm going to plug this thing in, this thing right here in for mu sub k. That's what's going to happen on the next slide, okay? So this is what I got. I got this, transpose this, and then we're going to plug in the formula for mu sub k, okay? All right, and technically I got a product of two things, and I'm going to end up having a double sum. So I'm going to use different subscripts, okay? I've got subscript m and subscript r for whatever reason. I think I'm following the book notation there, okay? And so here, I'm just expressing this distance, the distance from point n to the centroid of cluster K, all right? That's what this distance is, as kind of the product of all of these things where mu sub k has been replaced by this, okay? So if I do this, I get xn, and I apply the transpose, distribute the transpose, and I do, you know, and I FOIL first terms, and then the outer terms, then the inner terms, and then the last terms, okay? The first terms become xn transpose xn. The outer terms become, or the inner terms, I guess, become 1 over n sub k, summation of zm xn transpose xm, and the summation of the outer terms 1 over nk z r sub k xn transpose xr, plus the last terms plus, I'm going to get the double sum of 1 over nk squared, double sum xmk xrk xm transpose xr. Okay. It's a double sum because basically when we do this, you know, when I take this and I'm multiplying it by this, basically I have to take all of the possible x values, right? There's n of them, m equal to 1 to n. There's m of these x values, and I've got to kind of take every possible combination, right? X1 matched with x1, 2, 3 all the way up to n, x2 matched with 1, 2, 3 all the way up to n, x3 matched with, you know, all the way up. So we're going to have basically an n by n matrix here, and we're summing up all of the rows and all of the columns together. All right, and then this this should be mu sub k times xn. If we recognize this part times xm is equal to mu sub k, right? So if we go back, right, I've got 1 over n sum of 1 through n of the z's times x's. That is equal to mu sub k. And so even though these have different subscripts, sub m and this is sub r, they're both equal to mu sub k times xn, okay? And because of that, I can combine them, all right? And so I get this, and I'm going to just leave this term as is. All right. So what I've done is I've expanded the distance here into this. Okay. Now, why would I do this? This seems like I've made my life way harder than necessary. Oh, well, I guess before I go on, let me just pause here and just, is everyone okay with, I guess, what I've done? Is this like, let me give you the first quiz answer. It's 8th Wednesday. First quiz answer is B. B as in bear. Bear, Bruin, B. That's the first quiz answer. Okay. All right. So if you follow the kind of the math along, then you know that's fine and dandy and all. But again, the question, why? Why would I do this? All right. Why would I do such a thing? All right. This does not seem any easier than this. This, you want to say the square distance between x and mu? Sure, that's easy. I get that. Okay. So why would I go from this, which is easy to understand, into this, which is, I mean, like, I can follow the work, but why would you do this? The reason for this, okay, here's the impressive thing. This, we've expressed the distance from point N to the centroid of cluster K we've expressed that distance without mu sub k existing in here, okay? Without an explicit reference to mu sub k. So mu sub k is the centroid, okay? And we would normally, traditionally have to calculate this actual centroid. But I don't actually have to calculate the centroid itself. I can just kind of, I can find the kind of these inner products of x's and stuff, and I can still get the same distance. You know, I have to apply a bunch of sums and a double sum here, and that's a little bit of a pain, but I don't actually have to calculate mu sub k itself. And that's going to be useful because calculating the centroid maybe is easy if you have a simple transformation function, but if you have a function that transforms into infinite dimensional space, then calculating the centroid mu sub k is not going to be possible. So, so this is kind of the previous slide ends right here. Okay, this is the last line of the previous slide. And what we're going to do is we're going to say, what if we applied that transformation function phi to every single x value here? Okay, then what's going to happen? Then the resulting distance, okay, this distance can be expressed as a kernelized distance, and we can say, you know, if I apply phi to here and phi to here, then that's just going to be the kernel function of xn xn. If I apply the phi function, transformation function here, and phi to this x term, then we're going to get basically the kernel function applied to xn and xm. And if I apply phi to this term and this term, then we're going to get the kernel function of xm and xr. Okay, and that's what we have here. Okay, and so and because we use the kernel functions, we don't actually have to apply those phi transformation functions. We don't actually have to do that. The kernel function gives us the result of the inner product after we applied the phi transformation function, but we don't actually have to apply the function phi here. So so let me show you what we're going to do. Okay, we're going to redo k-means clustering, but this time with kernelized distances. Okay. And so, so the way the algorithm works is we're going to decide how many clusters k to find. We randomly assign points. So this part, the first two steps are exactly the same. All right. And before it used to be find the centroids, then reassign the points. Okay. Now we just reassign the points directly. Reassign values to clusters by associating the values in the data set to the nearest centroid using the kernelized distance. We're going to calculate the distance to the centroid in one step without actually finding the centroids themselves. Okay, so that's what this thing will allow us to do. We don't actually have to find mu sub k. We don't have to find the centroid to find the distance. We're just going to go straight to the distance. All we need are the values xn and the assignments that we currently have, and that's all we need. We just need the z's and the x's and the kernel function. We can get the distances without actually having to find the centroids themselves. So we just repeatedly reassign values to the centroids based on the current assignments, okay, without having to find the centroids. And then we repeat that until we reach convergence, okay? So yeah, no, we don't need to actually find the centroids. The kernelized distances will find the distances to the centroids directly without bothering to calculate the centroid itself, right? So, what I'm going to do is I'm going to just illustrate this on a very, very, very simple data set, okay? It's got a total of 8 data points. And I'm going to do the same. I'm going to do kernelized K-means clustering twice. First, I'm going to apply the transformation function phi to the data, and you'll see the data go from 2D into 3D. And then we'll do Euclidean distance in 3D and do our K-means clustering that way. And then the second time around, we are not going to apply the transformation function. We're going to use that kernelized K-means or kernelized distance formula or function, and we're going to find the distances to the kernelized centroids directly without finding the centroids themselves. So I'm going to do this twice, and you'll see it. Okay, so this is what our data set looks like. We've got these 4 points and these 4 points. And when I graph it, it looks like this. I got 4 points very close to the origin, 0, 0, and I got 4 points that are far away from the origin, okay? Now, if I used regular K-means clustering, regular K-means clustering will never put this point here in the same cluster as this point here, right? K-means clustering will always put points together based on Euclidean distance. And according to K-means clustering, this point and this point are very different. They're very far apart because their Euclidean distance is far apart. Okay, so it will never put this point in the same cluster as this point, okay? But maybe intuitively, when we look at this, we'd say, well, you know what? We shouldn't be just looking at its coordinate in two-dimensional space, but you know, it might make sense to cluster these points together and these points in a separate cluster, okay? So how can we do something like that, okay? Well, what we're gonna do is we're gonna apply this transformation. We're gonna go from a 2D coordinate to a 3D coordinate. So we're gonna add a third component, which will be x1 squared plus x2 squared, okay? And so here I've got x1 and x2 and x3 is x1 squared plus x2 squared. So I got 0.1 squared is 0.01, 0.1 squared is 0.01, and when I add those two together, I get 0.02. And if I do that to all of these, I get 0.02 for all of them. These ones down here, 2 squared is 4, 2 squared here is 4, and when I add those together, I get 8. And so in 3D, so these 8 points, when I transform them into 3D, become these 8 points, okay? And I can plot them, and it looks like this, and it's a little bit hard to see, so let me have, let me see if I can plot this. Okay, so this is what, oh, wait, hang on. Oh, sorry, I got ahead of myself. Okay, so so I put them into 3D, and then I started off with random assignments for the clusters. Okay, and so with the random assignments, we have 3 points. This point, 0.1, 0.1, 0.02, negative 0.1, negative 0.1, 0.02, and negative 2 to 8.0 in cluster 1, and then these other 5 points. This point and these points, we got 5 points in cluster 2, okay? And so when you plot those, the points in their cluster assignments, it looks kind of like this, okay? And so I've got, I don't know if you guys can see, I've got 1, 2, 3, 4, 5 in the red cluster, and I've got 1, 2, 3 in the blue cluster, okay? So these are the current initial random assignments. So we took our 8 points. So what we've seen, you know, when we plot them in the beginning, they look kind of like this, okay? And what we've done is we've applied a 3D transformation to it, right? We've gone from 2D into 3D, and that projects these into a 3-dimensional space. Okay, and so that's what it looks like here. And what we're going to do is we're going to calculate the centroid of each of those clusters, right? So centroid, the centroid of the first cluster is going to be the mean of this point, and this point, right? So the x1 coordinate we'll do 0.1 minus 0.1, which is 0, minus 2.0, which gives me negative 2, and I divide by 3, which will give me negative 0.667. Do the same thing here. I do this 0.1 for the x2 coordinate. I take 0.1, I add a negative 0.1, which cancels out. I add a positive 2.0. So I do 2.0 divided by 3 gives me 0.667. And then for the x3 component, I have 0.02, plus 0.02 plus 8. So that's going to be 8 plus 0.02 plus 0.02. So I have 8.04. I divide by 3, and I get 2.68. Okay, and so that's the centroid of the first cluster. Okay, and then I do the same thing with the second cluster, and I get this is going to be the centroid of the second cluster, and I can plot that as well. All right, so this is so I calculate that, and I'll calculate that, and let's go ahead and plot this. Okay, so again, here are the 1, 2, 3, 4, 5 red points, and 1, 2, 3 blue points, and these are the centroids. Okay, the centroids of red and blue are shown, and so you can see this is what it looks like. And so it's a little hard to see. I think when I plot them on this, it looks like this, but I think that's what this plot looks like. But you know, if you're able to rotate it, you can kind of see, yeah, it exists in three-dimensional space. And yeah, so here the centroid of these 5 red points is higher up, which makes sense. And then the centroid of the 3 blue points, because there's 2 at the bottom and 1 at the top, is lower down, right? So we got the centroids down here. So these are the centroids in three-dimensional space. And what we're going to do is we're going to reassign the points. We're going to take all of the points, and we're going to go through and say which centroid is closer. Is it this one or this one? Okay. So so this is the if you want to create kind of these little 3D plots in R, you would use plot 3D RGL, and you would use plot RGL as your command. And so we would go through and say, here are the centroids. Okay, this is that's the centroid. That's this blue lower centroid here. And we're going to say, okay, what's the distance from each of these points to this centroid, right? And what's the distance of each of these points to this centroid, okay? And so we do that, and we calculate, and basically we're going to do this minus this quantity squared, plus this minus this quantity squared, plus this minus this quantity squared, okay? And so we take the distance to this first centroid, and we get this number. And we take the distance from here to this centroid, and we get this number, okay? So, so that's basically, these are the squared distances to the centroids. And we say, okay, well, which one is closer then? Okay, well, all of these will say, all right, the blue centroid, for these 4 data points, the blue centroid is closer. And then we do the same thing for these data points up here, and we say, all right, here's this data point, which centroid is closer? Is the blue one or the red one closer? Okay, we look at this data point, is the blue one or the red one closer? Okay, it's a little harder to see, but you know, it exists in 3D space, and that's what we're doing. And so when we do that, we say, oh, you know what? Centroid 2, the red centroid is closer. So they all get assigned. So they get reassigned to here, okay? And so this is the result, okay, of what it looks like after we redo the assignments here. Let me see. Maybe that. Did that work? Oh, not yet. Jumping the gun. And let's go ahead and plot that. Okay. And so after I recalculate the centroids, we can see, oh yeah, now the centroid of these 4 points is up here, and the centroid of these 4 points down there is down there. Okay, and that's the centroid. And if we calculate the distance to the centroid, now it's very clear that you know, it's much closer to their respective centroids, and therefore the assignments will be unchanged, and we have reached convergence. All right, is that okay? So if you're following along, give me a green check. Let me know that this has gone okay. So what we've done is we've taken each of our 2-dimensional points, transformed them into 3D, and we calculated the Euclidean distance in 3D space. And we did our K-means clustering that way. And so that allows us to kind of cluster kind of these 4 points in the middle together into one, and the outer ones in different cluster, okay? Because we transformed them into 3D. And these are the distances we get. All right, so I'm going to do the same thing, same data set, same initial random assignments. And this time I'm not going to transform them into 3D. Okay, as fun as it was to play with our 3D plot, we're not going to transform into 3D. What we're going to do is we're going to use this distance formula, and we're going to calculate the distance to the centroid despite not actually finding the centroid itself. I'm not going to project the data into 3D. I'm not even going to bother calculating the centroid in 3D or calculating the centroid, but I'm still going to be able to get that distance without doing that, because we have re-expressed that distance as this kernel function, okay? And again, for our transformation into 3D, the kernel function that we're using is this, okay? And so, I'm going to have to create a kernel matrix, which is basically every value versus, every combination of the x's. Okay, so we've got 8 x values, and we're going to create an 8x8 kernel matrix, okay, to get this. Okay, so all I'm doing is I'm going to leave our x values as x1 and x2, and I'm not going to transform into 3D. I'm going to leave them in 2D. I have to create my z vectors. Okay, I'm going to create the z vectors, which contains the information about the assignments, and we're going to use this kernelized distance formula to find the distances. All right, so our kernel function, we're going to populate a kernel matrix with this. Okay, and so I get kind of my 8x8 kernel matrix, which doesn't have a practical meaning at this point, but is going to be important in calculating these distances. Okay, and then if I do a double sum of this, taking each z and z here, okay, zm for zm in 1 through n and zr in 1 through n. Okay, basically I start off with a double sum equal to 0, and I'm going to just keep adding each term here, and I'm going to go for r in 1 through n. And I'm going to basically find the kernel matrix m comma r, multiplied it by za sub r. And I do that for r in 1 through n, and then I do it for m in 1 through n. Okay, so that's the double sum, and this is going to be the quantity here. This can also be achieved with this. You don't have to worry about this, but you can get the same value by kind of taking the outer product of z and z. And then, and here we are going to find the distances to A, okay? And so what I do is I'm going to take the kernels. So for all of our n values, we're going to take the kernel n, and then we'll do this. And then we add the double sum, and then we're going to get all of these distances, okay? So note these distances, okay? I've got 7.984, 8.251, 7.717, 7.984, okay? These are the distances from each value, n, x sub n, to the centroid after we've transformed it in 3D space. So I'm going to go back to slide 35, and this was, we calculated the centroids, and just using the Euclidean distance, we calculated the Euclidean distance from this value to this centroid, and we got that distance to be 7.984. And then we calculated the distance from here to this centroid, and we got 8.251. And this one was 7.717, 7.984. And if I go back, we get the exact same values. 7.984, 8.251, 7.717, 7.984, 37.19, so on and so forth, okay? I do the same thing for the distances to centroid B, okay? And if I compare this to the slide, again, these distances, 23.264, 23.104, 23.424, 23.264, 23.104, 23.424, same distances, okay? So we're able to get these distances to the centroids, the same values, okay? And here I put them all together. We're able to get these same distances without having, so earlier I had to calculate, transform them into 3D and calculate the centroids. I can get those same distances, okay? So look at these numbers here. And look at these numbers here, they're exactly the same. I can get the same distances without calculating the centroids, okay? Just by using the crazy formula, right? By using this crazy formula, I can get the distances to the centroids without calculating the centroids themselves, without transforming the data into the higher dimensional space, okay? And if I redo these, so basically, using this, we can say, all right, which ones are closer? And we can say, all right, all of these will get assigned to cluster 1, and all of these will get assigned to cluster 2. Okay, and I messed up this slide, but we can recalculate the centroids to their recalculated to the new the distances to the centroids, and we're going to get the same values that we got earlier. Okay, so it's kind of neat. We're able to get the distances to the centroids without actually without transforming them into higher dimensional space, and without actually calculating the centroids themselves. Let me do another example here, okay? And okay, so here what I have to do is I'm going to start off with an example. Sorry, give me a second here. Okay, so here's kind of our just some toy data set that we're going to play with. And what we can see is we've got, if we said make 2 clusters, we would probably intuitively we would say, all right, the ones in the middle belong together and the ones on the outer rim belong in a different cluster. But if we used K-means clustering, it's not going to work, right? So here I tried using K-means clustering, and it says these points belong together and these points in black belong together, okay? And it will never, K-means clustering will never put a point up here in the same cluster as a point down here, because it's using Euclidean distance, and in Euclidean distance in two-dimensional space says this point and this point are far apart, therefore they are very different from each other. Their Euclidean distance is far apart, they're very different, they should never belong in the same cluster together. So K-means clustering by itself is not going to work for this data. So what we're going to do is we are going to apply a transformation function, okay? And here I'm going to use the Gaussian kernel, the radial basis function. And so again, what this is doing is it's transforming the data into infinite dimensional space, and but we don't actually have to transform it into infinite dimensional space. We can just get that kernel value, which is just going to be the inner product after and I do this, okay? So I don't actually have to transform it into infinite dimensional space and get the sum product. I can just use the kernel function, but it's equivalent to getting the inner product after transforming it into infinite dimensional space. So if I use that, I can try doing K-means clustering using the kernelized distances. And so here I start off with random assignments. And then we say, all right, transform this into infinite dimensional space, calculate the centroids, and reassign the points to the nearest centroid, okay? Again, we can't really visualize what the data looks like in in this infinite dimensional space, and we cannot know the actual centroids, but we can still start to cluster them using points that are using the Euclidean, using the distance metric that we found. Okay, so so this is after one iteration. It's hard to know what it's doing. Okay, after another iteration, it looks like this, and then after a few more iterations, it has converged, and indeed, it has put the these points together in one spot and these points together in another cluster. Okay, so it has succeeded, but again, and it's using the distance to the centroid in that higher dimensional space without actually finding the centroids themselves. And I know that's a weird thing. Like, how can you find the distance to the middle if you don't even know where the middle is? So here, I give a silly example, but so imagine we're trying to cluster actors together. Okay, so so here I've listed off some actors: Chris Evans, so this is Chris Evans, Chris Hemsworth, who plays Thor, and Jason Momoa, who plays Aquaman. And okay, so so let's say we have these actors. We have Jason Momoa, Chris Hemsworth, Chris Evans. Okay, and then we also have other actors. We'll say we've got Joseph Gordon-Levitt, Jesse Eisenberg, and Adam Scott. Okay, so here's Adam Scott, here's Jesse Eisenberg, and here's Joseph Gordon-Levitt. Okay, and okay, so a person is a complicated character or a complicated thing, and a person might be defined on, like, I don't know, hundreds of different dimensions, right? If we wanted to try to quantify what a person is, right? But then we want to try to cluster actors together and stuff. All right, and so we would probably put Joseph Gordon-Levitt, Jesse Eisenberg, and Adam Scott. So Adam Scott's from Parks and Rec. Jesse Eisenberg was in The Social Network as Mark Zuckerberg. And Joseph Gordon-Levitt, he was in 500 Days of Summer, Inception, a few different movies and stuff. And then, you know, Chris Evans, he's Captain America. Chris Hemsworth is Thor. Jason Momoa is Aquaman and Khal Drogo. They're different, right? But what would the centroid be, right? Like if I cluster these three together, and I cluster these three together, okay, if I cluster Chris, and Jason together, and these other actors, if I cluster them together, what is the centroid? The centroid would be the average of these people, and like, what is the average of a person? Like 3 different people. It doesn't quite make sense, all right? But what you can do is you can still kind of put them together by kind of saying how similar or how different are they, right? Like if we know these 3 belong to a certain cluster, and then these other 3, the Chris Evans, Chris Hemsworth, and Jason Momoa, belong to a different cluster, then if we get a new person or something and we want to try to cluster it, we can just measure the similarity between this new observation and the data points that already exist in our data, and measure similarity that way without actually having to find the centroid itself. Okay, it's a bit of a stretch of an example, but it's kind of the idea that even though it's not really possible to find the centroid of 3 different people, we still get a sense that, you know, these three belong together and these three belong together if we're going to cluster them. And so that's kind of the idea there, that you can still get a sense of how different, or, you know, what's the distance to a centroid. How, are they different without actually finding the centroid themselves using, you know, this kind of crazy formula here. Okay, that's all I've got for you guys today. So we'll end there. Oh, the second quiz question is E as an elephant. So E as an elephant is your second quiz answer for today, and we'll wrap it up there, and we will see you guys on Friday. All right. Okay, let me stop the recording.